Hi Rockridge, this is Mrs. Berger, and today we are going to cover the lesson on solving radical equations. So because I have noticed that a lot of folks could use some extra time with the simplifying, the adding, the subtracting, the multiplying, and the dividing, I am going to go ahead and record solutioning the warm-up for today as well. So if you have already understood the warm-up, you can go ahead and fast forward through this lesson to the solving part. But I'm going to walk through the warm-up and then we will start on solving radical equations. We're going to break this topic into 2 days. So today is the first part of solving radical equations, and then we'll have another day of solving radical equations so we can get this really nice and strong in our minds. Okay? So let's hit the warm-up. The warm-up is, of course, review material from the beginning of the unit. And so let's remind ourselves what we do when we have a rational exponent or a fractional exponent. Remember that the number on the bottom is the version of the root, so pretend like there's a little invisible 2 here. And the number on the top of the fraction is the power that you're bringing things to. And then we go ahead and simplify where we can. So the square root of 4 is 2, and we're bringing that to the power of 3, so that makes it an 8. Okay. On number 2, we have a negative fractional exponent. So the first thing I suggest you do is put this whole guy on the bottom of a fraction so that you can turn that exponent into a positive 2/3. And then while you're working on this on the bottom of the fraction, you take this fractional exponent and you turn it into root 3 of 27 raised to the 2 power. To continue simplifying this, you take the third root, or the cube root of 27, which is of course 3. And now that that's simplified, you're going to square it. So the final on this one is 1/9. Don't forget, I keep seeing folks forget, this first step that they did, they put it on the bottom of a fraction. So your final answer, all that work that you do, should be on this bottom of the fraction. Okay. Number 3, I'm going to go ahead and wipe this and make myself a little bit of room here. Number 3, I've got a bunch of different exponent rules in play here. I'm going to choose to distribute this. There's a couple of different ways you're going to do this, but I find it easiest to start by distributing this power to everybody. So you're going to give that power of -2 to everyone on the inside. 2 to the -2. X to the -6, remember, power of a power you multiply. Y to the +2 over 3 to the -2, x to the -2, y to the -4, because 2 times -2 is -4. Now there's a couple steps you can do here in different order. I'm the type of person that likes to make negative things positive as my first step, so I'm going to make all that happen. So this 2 to the -2 I will move to the bottom. This x to the -6 I'm going to move to the bottom. And remember, when you flip to the other side of the fraction, you turn it to a positive. This y squared can stay up here. He's already positive. He can stay where he is. This 3 to the -2 needs to move to the other side. This x to the -2 needs to move to the other side. And this y to the -4 needs to move to the other side. At this point, I can start combining things. And again, if you have a different order that you'd like to follow, that's fine, as long as we end up in the same place. So 3 squared is 9. X squared. When I have y squared times y to the 4th, base to a power times base to a power, I add the exponents, so that's y to the 6th over 4x to the 6th. My last little step here, sorry about that, I forgot to give x squared there. My last little step here is to take care of the fact that I've got x squareds and x to the 6's. Now the way I think about this, so that I can make sure I keep the signs straight, is I say I've got x squared, and this 6 is minus 6, right? Because you take the top power minus the bottom power. Okay? That's how I do it, just to keep my signs straight, so I'm not flipping sides and changing signs and all that kind of stuff. So now, of course, we all know that 2 minus 6 is -4. All this other stuff stays the same. And then finally, we fix the fact that this is a negative exponent by moving it to the bottom. And everyone else stays on their side of the fraction. Again, there are definitely faster ways to do this. You can combine steps. You could have combined these x's in this first step here instead of dragging it out. I just do this moving the bottom to the top step here just because it keeps the sign straight in my head. Okay. We of course check to see if we can reduce 9/4. We can't. We check to see if there's anything else to combine. There isn't, and that will be our final on that one. Okay. So make sure you've got these power rules nice and straight in your head. I'm going to wipe the board again and take a look at the next problem that I have. It is a FOIL problem. I'm multiplying this complex number by this complex number. I've got radicals involved, so we'll see how these play out. Okay? So FOIL, first times first, outer times outer, inner times inner, and last times last. Remember, you multiply the things on the outside by each other, and you multiply the things on the inside by each other. And now we'll try to combine what we can. 10 square roots of 3 and negative 3 square roots of 3 is 7 square roots of 3. Minus 2 times the square root of 9, of course, is 3. So I've got 15 plus 7 square root of 3 minus 6. So the last thing I can combine here is 15 minus 6 is 9 plus 7 square roots of 3. Nobody else can be combined. Please do not combine this 9 and this 7. Do not do that. You have 9 and you have 7 square roots of 3. Those are not like terms. They do not get combined. Okay? And then finally on number 5, this may look like you distribute this 2 here, but you do not. These things are not being multiplied together. Okay? Unless they're being multiplied together in here, you're not allowed to give everybody this power of 2. So try to think about what you need to do here. You actually need to make 2 of these and FOIL them together. If you already knew that, congratulations. That's excellent. Make sure you make 2 of them and FOIL them together. Do not distribute this 2 to everybody. Unless all this stuff inside is being multiplied by each other, you're not allowed to distribute. If there's adding or subtracting going on, you have to make 2 of these and then square them. Now we know how to do this. First times first, outer times outer, inner times inner, and last times last. We're going to combine where we can. Let's see. Square root of 4 is 2. There are 8 square roots of 6, and then plus this 3. I have 16 times 2, which is 35. Oh, sorry. That's 32, and I'm getting ahead of myself. So 32, and then plus the 3, and then plus 8 square roots of 6. So that's 35 plus 8 square root of 6. Okay. And we'll check in here to make sure we can't break anything out, but 6 can only get broken down to 2 and 3, so there are no other perfect squares in there. If any of that went too fast for you, please pause the video and go back and watch it again. I want you to be really nice and strong on these skills. Alright, last couple of problems on the warm-up. I have to distribute this into here, and then I have to see what I can combine or if there's anything else I need to break out. So let's go ahead and distribute. So negative 12 times the square root of 12 plus 20 times the square root of 18. That's my distribution step. And then this mess of a thing, 5 times the square root of 48, is sitting out here. Now, I want to break out what I can, because clearly, square root of 12, square root of 18, square root of 48, none of this can get added together or subtracted together. So nothing can be combined yet, but I'm sure if I break some things out, I will be able to combine some things. So I'm looking inside here to find the biggest perfect squares I can. And I found some. So the square root of 4 is going to be able to come out. The square root of 9 is going to be able to come out. The square root of 16 is going to be able to come out. So I'm going to have negative 12 times 2. And the square root of 3 is left behind. I'm going to have 20 times 3, and the square root of 2 is going to be left behind. And then I'll have 5 times 4, and the square root of 3 is left behind. If you didn't follow that, or if that was going too fast, please pause. Make sure that you can do this skill. This is a super important skill for this unit. All right, let's go see what we've got going on here. I've got negative 24 square roots of 3. I've got 60 square roots of 2. And I've got 20 square roots of 3. This guy doesn't look like he has any friends, but this first one and this last one can be combined to make negative 4 square roots of 3. And then these 60 square roots of 2 are just going to be on their own. Can't break anybody else out, can't combine them with anybody else, so I'm finished there. Number 7 is an interesting one. Okay, we looked at number 7, and there are a couple of different ways to go through this. I'm going to go through the more sophisticated way first because it takes up less paper. And then I'm going to go through the somewhat less sophisticated way second. So you have two options at your fingertips. So if I take number 7, and I notice that number 7 has, within the radical, things that are divisible by each other in both of these radicals, it would be super useful in this particular problem to think of this as 3 times the square root of 40 over 8 plus 2 times the square root of 24 over 8. Okay, you can do that. The properties of these radicals work that way. This is basically two different fractions, this fraction and this fraction. Just like 1/2 plus 3/2 is the same thing as 1 plus 3/2. Okay, just like that, back from our early fraction days, these fractions can be broken into these two parts, and that is super duper useful. Because 40 divided by 8 is 5. 24 divided by 8 is 3. So that is the super sophisticated way to do that problem. If you don't have that understanding of how these work, you can absolutely make use of what we learned last class in Rationalizing Denominators and treat this problem a little bit differently. You can say, well, this radical on the bottom is my troublemaker, and so I am going to counteract that troublemaker by multiplying by the square root of 8. Remember doing that? We're going to rationalize this denominator by multiplying by the square root of 8. If that's the first thing you thought of when you came upon this problem, that is perfectly fine. Perfectly fine. You will eventually get to that same answer we got through the pink way. Okay? So as you know, if you multiply square root of 8 by square root of 8, you get the square root of 64, which is, of course, 8. And if you multiply the top by square root of 8, you're going to have to distribute the square root of 8 into these two terms. Okay? And you're going to have some big numbers. So let's watch what happens. This first thing becomes 3 times the square root of 320 plus 2 times the square root of 192. And as I'm sure you've guessed, we need to start breaking things out of here so that we can simplify. So within 320, I know that I can take a 64 out of here. If you go off to the side and build a giant factor tree, at the bottom of this there will be a 64 in there. So if I take the square root of 64, obviously that's 8. And if I divide 320 by 64, I'm left with 5. And again, if you need to pause the video and make some factor trees for 320, please do so. Okay, you'll need to do it on the test anyway. So if you can't come up with 64 is sitting inside 320 and comes out as the square root of 64 is 8, pause the video and do that for yourself. And then plus 2, and if I look inside 192, once again I will find that there is a 64 in there. 64 times 3 is inside 192. Okay, so within 192 there's a 64 times 3. So if I take the square root of 64 once again, I can bring that outside and I leave behind that 3. Now, once again, we always look for simplification. And before I start multiplying 3 times 8 and 2 times 8, I'm just going to go ahead and take 8 out of these places, because we need to find a factor that is in all 3 places, and I did. I found an 8. So I'm left with 3 times the square root of 5 plus 2 times the square root of 3, which of course is what we got in the first method. Okay, so we will get there. We will get there. We'll have a little bit of extra reduction to do. We'll have a little bit of extra breakouts that we need to do, right? 320 can be broken into 64 and 5. So we have a little bit extra work to do, but we should get to the same exact place if we're doing it correctly. All right, that is our warm-up. Again, please pause and rewind as many times as possible. That is a great problem set for getting us prepared for those types of problems. Now, solving. Your goal in solving radical equations, and radical equations, we just mean there's an equal sign and somewhere in the problem there's a radical that we need to take care of. Your goal is to isolate the variable. Isolate x, isolate b, isolate a, isolate the variable, right? Find out what it equals. And we always do PEMDAS in reverse when we're trying to isolate things, right? We take care of adding and subtracting, multiplying and dividing, the exponent. So if I look at number 1, the variable I need to isolate is the letter b. And there's nothing out here that's being added or subtracted. Somebody must have subtracted a 3 to this side already. There's nothing being multiplied out front, so there's no adding or subtracting or multiplying or dividing to be done. But there is an exponent I need to take care of. This radical is actually an exponent. Remember, b minus 1, the square root of b minus 1, that's the same thing as b minus 1 to the 1/2, right? Those are the same thing. So this exponent that this radical is going to have to be counteracted. I need to take care of that. I need to do PEMDAS in reverse. So to counteract the square root, to counteract the root of 1, the power of 1/2, I'm going to bring it to the 2 power. That will take care of that. That will make that radical disappear. And whatever I do to the right, I have to do to the left. So now I have 9 equals b minus 1. Because I took care of this root, this power of 1/2, by raising it to the 2 power. Remember, power of a power you multiply? When I raise this to a 2 power, this goes away, right? If I raise this to the 2 power, it goes away. It turns into 1 over 1. So now I've counteracted that power, and now I'm just left with 9 equals b minus 1. And we know how to do this. We learned it in Algebra 1. Add 1 to both sides. So b must equal 10. If you don't trust yourself with your math, you can always plug 10 back into b for the original equation and make sure that it's right. 10 minus 1 is 9. The square root of 9 is 3. We did it correctly. Now we can go with this radical here. Obviously, this can also be written as x over 2 to the 1/2 power. Same thing. We're going to take care of this by raising it to the 2 power. Raising it to the 2 power. And whatever I do to this side, I have to do to the other side. So I've got 4 equals x over 2, because that 2 power negated my radical. And of course, we know how to solve this. We multiply both sides by 2 over 1 to take care of that fraction. So x equals 8. If we were to plug 8 back in for x, 8 divided by 2 is 4. The square root of 4 is 2. So we did a good job. So of course, you probably trust me at this point. I don't have to prove it to you. We will counteract this radical by squaring it. Whatever you do to the left, you have to do to the right. So now I have negative 8 minus 2a equals 0, because 0 squared is 0. Add 8 to both sides, divide by negative 2. So your variable isolated is a equals negative 4. If you plug that back in, you will get the right answer. If you have time on these quizzes and tests, I always urge you to plug your answers back in for the variables to see if you did it correctly. Now this guy, don't panic, same plan. To get rid of this radical, I'm going to square it. Whatever I do to the left, I do to the right, which is super convenient, because now I'm left with 2m minus 6 equals 3m minus 14. Super convenient. Now I just combine like terms and solve. Subtract 2m from both sides. Add 14 to both sides. M is 8. If you were to plug 8 in here for m and here for m, you will get a true statement. So we've done it correctly. Same thing on number 5. We are going to take care of this by raising it to the 2 power. Whatever you do to the left, you have to do to the right. So now I have 8k by itself here, and I've got k squared over here. Please do not panic. I know you've got k's in 2 places. Don't worry about it. Get everybody on one side. Subtract 8k from both sides. Do you remember how to solve these from Algebra 1? We can factor a k outside. Okay. Factor a k out. Leave k minus 8 behind. Do you remember what to do when you have these two things set equal to 0? You take each factor and set them equal to 0. Each factor, set them equal to 0, and then solve. This is already isolated, so here's one of my answers. Add 8 to both sides. There's another answer. If you don't remember solving these from Algebra 1, please pause and replay that. You should be pretty comfortable with this skill set. So we actually have 2 answers for k on this one. If you were to plug 0 in for k, you'd have a true statement. If you were to plug 8 in for k in the original, you would have a true statement. So those are the 2 answers that will get you a true statement for that. Number 6, remember this 1/2 power, that's the same thing as a square root that we had in these previous problems, right? Square root, 1/2 power, same thing. So we're going to use the same plan to solve these. Raise it to the 2 power. Same plan. So raising it to the 2 power gets rid of this nasty power, and we're going to just be left with 3a minus 1. Raising it to the 2 power is going to take care of it, leave an a behind. Subtract a from both sides. Add 1 to both sides. Divide by 2. Your solution is 1/2 for a. If you were to put 1/2 in for a, you'd get a true statement. Let's step it up a notch here with number 7. Number 7 is a cube root. How do you think you counteract a cube root? It's very similar to how you counteract a square root. Instead of raising it to the 2 power, we're going to raise it to the 3 power. Because again, this is just y minus 2 being raised to the 1/3 power. Remember? That's how you convert these radicals, right? So this is the same thing. Y minus 2 to the 1/3 power is the same thing as the cube root of y minus 2. So to counteract that, we're just going to raise it to the 3/1 power. That's why we're raising it there, okay? So to get rid of this cube root, we're going to raise it to the 3 power. Whatever you do to the right, you have to do to the left. So now I have 27 equals y minus 2. So y must equal 29. If that went too fast, this explanation up here was confusing, pause, rewind, make sure you're super comfortable with the fact that the cube root of y minus 2 is the same thing as y minus 2 to the 1/3 power. And again, if you plug 29 back in here for y, you will get a true statement. All right, let's work on this last one here before you try the practice on your own. A little bit of a more difficult problem here. I have this stuff being brought to the 3/2 power. How do you think you counteract the 3/2 power? You can't just counteract it by bringing it to the 2 power. That won't fix everything. But if you raise it to the 2/3 power, remember what happens with reciprocals. If you multiply 3 times 2 and 2 times 3, those go ahead and cancel out. So that's the tool you're going to need to use here. And this is definitely a little bit more advanced for today. But if you're bored, this is a great problem to work on. Whatever you do to the right to counteract this power, you have to do to the left. So on the right, you've now broken this 2a minus 1 out, and all those powers went away. Now remember what happens over here. A to the 2/3 power, That's the cube root, 8. 8 to the 2/3 power. That's the cube root of 8 raised to the 2 power. Cube root of 8 is 2 squared equals 2a minus 1. 2 squared obviously is 4. So 4, and I'm going to add 1 to both sides. So 4 plus 1 is 5. And then I'm going to divide by 2. That's my solution. A is 5 halves. If you plug 5 halves in for A in the original equation in black here, you will get a true statement. And I encourage you to always try that. Now, I'm going to set you free to go ahead and work on the 7 you try problems. Definitely check them against the key or with your teacher. If you need to go to Math Lab on any of this stuff, bring your problem set and make sure that you understand how these are working. We want to get these basic skills of solving done so that when we get day 2 of solving, we feel super comfortable with it. Okay? Thanks so much.